All right. Now that you've finished your assessment on your solving exponential and logarithmic equations, we're going to do a little graphing calculator work just to remind you that when you have equations, you can graph on the calculator to get approximate solutions as well. So if you have your own graphing calculator, you should grab it now. And if you don't have one, you can access the one that's on the Park NJSLA website. The directions for accessing that are still posted in Google Classroom under the general resources, general information and resources. Okay, so we're going to use a graphing calculator to solve this equation. Before we do that, first thing to just kind of think about is why we would want to use a graphing calculator to solve this. If you think for a minute about trying to solve this algebraically, you could rewrite this as log base e of 2x minus 1, because you already have your log function isolated, and then switch over to exponential form. There's your base, your exponent, and your other guy. And then you're stuck. You can get this x by itself by moving the 1 over by adding it and then dividing by 2, but you have not successfully solved for x because you still have an x in here. So solving for x, you can't have an x on the other side still. So we don't know how to solve this one algebraically. Neither do I. So what we want to do instead is we want to use a graphing calculator to solve. There's a couple ways to do that. Here's one way. One way to do this is to graph the left-hand side and graph the right-hand side and find out where they equal each other. And that's my favorite method, so I'm going to show you that first. So if I graph, and I'm in Zoom Standard, there's my log graph. The log graph really should keep coming down more toward this, but as we've shown in the past, the calculator has trouble graphing log accurately when it gets toward where the vertical asymptote would be. So just be aware that it doesn't really stop right there. It actually continues down toward a vertical asymptote. But regardless of that part of the graph, what we're interested in is the point where those two intersect. So if we do second trace intersect, the calculator will put us on the log graph. See, it says first curve, y1. And you can't see the cursor right now because it's put us on the y-axis because it says x equals 0. So just go a little bit to the right. And once you get a little bit further to the right, because that's the area where the graphing calculator has trouble because of the asymptote. So once you get a little bit further to the right there, you actually are on your log graph. Go as close as you can to the point of intersection and hit enter. The calculator will put you on the second curve. See how it says y2? Get as close as you can. I think we're already there, so I'm just going to hit enter again. And then take your guess. You'll know you're finished with this process when it says intersection. And what we're looking for this answer is we're going to round to 3 decimal places here. So it's 1.562, 0.753 is the point of intersection. But the answer to this is only the x coordinate. So when you use this technique to solve an equation graphically, of graphing the left-hand side and the right-hand side, you only want the x coordinate of the point of intersection. Because think about solving this equation. You're not looking for any y's. You're looking for an x that you can plug in here and plug in here that will make the two sides equal to each other. So that's the x that will do it, approximately. All right, so that's my recommended method. Graph the left-hand side, graph the right-hand side, and find where they intersect. Just to remind you, you do have other ways to do this graphically. One way to do this is to get all the terms onto one side. So we can move the 4x over by adding it to the other side and move the 7 over by subtracting it. And then since one side is equal to 0, we can graph this and then find the x-intercepts. So that's what I did here. So I have the left-hand side typed in. And now it's only one graph that I'm looking at because the other side is 0. So if you're solving graphically when one side equals 0, this is when you want to find the x-intercepts. So to do that, it's second trace 0. And to do second trace 0, you're going to do let me restart that. I did it kind of fast. If you're doing second trace 0, it says first left bound, so make sure you're to the left of the x-intercept. And then it says right bound, so go to the right of the x-intercept. You don't have to be exactly where I am, but make sure you're to the right of the x-intercept. And then get as close as you can to take your guess. You know you're finished when it says 0. And you see here you have 1.562, the same answer that we got using the other technique. So my preference for this topic is to graph the left-hand side and right-hand side find the point of intersection, and the x-coordinate is the answer. So that's the technique I'd recommend. As an alternate, you can move everything to one side and then find the x-intercepts. If you prefer that, that's fine. Okay. Here's our next example. Here's our next one. We're going to solve this equation right here. And again, this is one that I probably would not really be able to do algebraically, so we're going to go ahead and graph. And if you notice, I already have that set up. We're just going to do the one technique for this one. We're just going to graph the left-hand side and the right-hand side and find where they intersect. So by the way, if you notice what I'm doing here, I had everything set up already. And you can do that without showing those graphs by deselecting or selecting the equal sign. So if you notice before, see for that first example we did, I had those two selected. So those are the two graphs that showed up. The other equations were still stored in the calculator, but they did not appear because they were deselected. So if the equal sign's not darkened, it'll store that equation there, but it's not going to graph it. So what I want right now is this e to the x over 3 plus 1 minus 5 and x plus 2. And the benefit of knowing that you can leave those equations in there is if you're ever taking a test or a quiz or an AP exam and you want, or even doing a homework assignment, and you think you might want to go back and look at the graphs from a previous problem, you can store the equations in there. You don't have to erase them. And then you can go back to them without typing them in. And that's also great when you're doing homework, because if you ever had trouble with a homework problem when we're in school, you could come in the next day and show your teacher what you'd graphed, and we could figure out what went wrong. So anyway, let's go ahead and take a look at this graph. I'm in Zoom Standard again. So here's my exponential function, and here's my linear function. This is just linear. It's a line with a slope of 1 and a y-intercept of 2. And this has 2 points of intersection. So what we want to do is find both of those solutions. So second trace intersect, and I'm going to go for this one first. Right now I'm on y3, the exponential function. You can see the equation here, y3, the exponential function. That's the first curve for this. I hit enter. Now I'm on the linear function, the second curve for this, these two equations. And now I take my guess. So this point of intersection is 4.265. And I don't even need the y-coordinate, because if you think about what you're really solving here, you're looking for the x that you can plug in here and here. That makes these two sides equal to each other. So there's one value. To get the other value, we'll do second trace intersect again and go find out what that point of intersection is. And what we get over here is x is about negative 6.7. That 9 is going to round up because of the 6, so it's going to be 10 or 1. So you can put negative 6.71 or negative 6.710. Either one's fine if we're rounding to 3 decimal places. All right, and then I have two more quick ones down here. And I'll just show you both. And what, here I put an inequality. So one side is 0, and the other side is has an exponential involved. And what we want to do to solve that is we want to graph this function. When you go to do that, make sure you put a negative here. Don't put a minus. If you put a minus, you're going to get a syntax error, because when it's the very first thing in the equation or expression, it needs to be a negative instead of a minus. All right, so you're putting the negative there instead of the minus operation. And here's the graph we get. So when you have greater than or equal to 0 or less than 0, what you want to think about in that scenario is above and below the x-axis. So this greater than or equal to 0 means above or on the x-axis. And then for this one, I have the same expression on the left-hand side, but I want to know where we're below the x-axis. So if you take a look at my graph, this is the point where things change. To the left of this, we're above the x-axis. To the right of this, we're below the x-axis. So to find that point, we're going to do second trace 0. That's how you find an x-intercept. And we need to be to the left, to the right, and then take a guess. Now, when it says left bound, remember, you don't want to think above or below. You want to think of left or right. So right now, I'm to the left of the x-intercept. And now I go to the right. You don't have to be exactly where I am, but make sure you're to the right of the x-intercept, and then take your guess. So the x-intercept here is about 2.192. That's where the graph has an x-intercept. And to find out where we are above, that's everywhere to the left of this. So if you're going to do an inequality, it would be all x's less than 2.192. And that is just an approximation because I did round that, but this will work for us. Or if you want to use interval notation, it would be negative infinity to 2.192. Infinity and negative infinity always get parentheses. And I put parentheses, whoops. I did both of these wrong. This is one said or equal to. So I want that point because that's on the x-axis and everything up here. So that point and everything up here. So the inequality should be inclusive, not strict like I had it before. You want the or equal to. So x less than or equal to that approximation. And then negative infinity up to 2.192, including that because we want on. And again, these are approximations, so it's not perfect, but it's the best we can do at this point in time. And then for below the x-axis, if you want to use an inequality, you want everything to the right of this x value. So you want x's that are bigger than 2.192. And if you want to do that in interval notation, this time you actually would use parentheses on that 2.192 because we don't want to include that. That's where we're on, not strictly below or less than, out to infinity. And it is infinity, not negative infinity, because we're talking about to the right forever. So if you were thinking negative infinity there, you're thinking down by accident. But the interval notation uses x values, so it's to the right forever. All right, thanks for watching. And remember, these techniques work for exponential functions. They work for log functions. They work for any kind of function you might encounter. Cubic functions, square root functions, linear functions, quadratic functions. So that's one thing that's really nice about the graphing calculator is if you have a graph that you're not familiar with or something that you can't solve algebraically on your own, the calculator has the potential to give you a decimal approximation.